Can you believe it? Can you believe that it's the very last screencast? The very last screencast of the whole entire semester. It's kind of crazy.
Crazy.
It is pretty crazy. And for this screencast, we're going to be proving a particular crazy thing. You know what we're going to be proving? I don't even care if this goes over time. We're going to have fun with this, right? I just want to say thank you for being an amazing teacher. I've loved this class, and I really appreciate you grading everybody and giving everybody feedback, and spending the time like detailing everything out instead of just being like, nope, you did it wrong. um but no, I really like the what's it, oh yeah, the outcome based learning style. And this whole class was pretty awesome. So we have a particularly interesting thing that we'll be proving today, and it has to do with the cardinality. It has to do with the cardinality of sets, and in particular, it has to do with the cardinality of a set that we'll call C, and we'll use some fun colors today. So C is going to be a big set, and it contains a bunch of sequences, and these sequences are binary strings. So we have a bunch of binary strings, and they're infinite, so on and so forth, right? So they go on for infinity, and we have an infinite amount of them. And C is the set of every single binary string that we can think of, right? So we're going to prove that this is uncountably infinite, and we're going to do so using magic, and the proof is left as an exercise with the grader. Just kidding. That would be fun, though. So first of all, let's consider a random string, 0, 1, 1, 0, 1, 1. I feel like I'm a computer right now. And we're going to go on for infinity. And then we're going to have something like 1, 0, 1, 1, 0, 0, so on and so forth. So these are all subsets. And let's label this sequence 1, let's label this sequence 2, then we have a sequence 3, sequence 4, so on and so forth until infinity, right? I'm kind of sad. This is really sad, this is the last one. I feel like, Time Academy has lived a good life. I've provided free education to millions around the world that are able to access YouTube. I mean, the only people that watch the videos are my family and Wyatt's family. But I mean, it could go out to millions if they wanted. So now, let us define a sub I. So these are all of our different sets, and let's name all of these sequences a sub 1, a sub 2, a sub 3, a sub 4, etc., right? And these can be arbitrary. These can literally be anything we want them to be. So let's just say a sub 1 equals a first element of a sub 1, and then it equals the second element of a sub 1, then it equals the third element, then it equals the fourth, so on and so forth to infinity, right? And we can copy this. I'm not going to lie. I'm not going to rewrite the whole thing. I'm just going to bada bing, bada boom it. That's what the New Yorkers say. Bada bing, bada boom. And then it magically happens. Magic. I bet you didn't even catch that. You didn't even catch the sleight of hand there. Although the real trick, the real magic trick here is that I actually made a copy of it. But you had to be really paying attention. You had to be paying close attention to see that. Okay. Let's do this rigorously now. So, let a sub 1, a sub 2, a sub 3, all the way up to a sub I, and then all the way for infinity, be defined as A11, A12, A13, so on and so forth, A21, A22, so on and so forth, all the way to infinity. And at this point, what we can do, we can say that C is the subset of B sub 1, B sub 2, B sub 3, so on and so forth. Actually, we'll use A1, A2, A3. Keep it, going. And at this point, what we can do, we can say that A sub I, so we're basically going to make a Kronecker delta function. We're going to say it's 0 such that A sub I equals 1. It's 0 if that, and it's 1 if A sub I, that looks like a sigma, equals 0. So at this point, what we're going to do, what this is basically saying, is we're going to look at the indices where they're both the same. And then we're going to generate a new sequence based off of the opposite of that. So this is kind of a clever trick, because what we're saying, if we have a 0, 0, 1, 0, then it's going to turn into a 1, 1, 0, 1, right? But here's the clever thing. The next part, whatever we define that to be, it's going to be unique. And then it's going to generate a unique string from that. And because of that, that means that whenever we think that we finally pinned it down and that we've listed out every single binary sequence that we can think of as a natural number, then we can just go across the diagonals, create a new one, and it all falls apart. And we can do this infinitely. So that's already a proof that it's, uncountably infinite. Although, we can either go big or we can go home. And honestly, I kind of want to go big. So if we go up here, I decided that it would be kind of fun to define a binary function. So, and I'll switch this to A for consistency. So we have A sub n and then A sub l. So A sub l represents the binary representation of each string. So at this point, A sub 0 would equal, as you see, like 0, 0, 0, 0, 0, so on and so forth. A sub 1 equals 1, 0, 0, 0. A2 equals that. Binary. I mean, computer science and math are basically the same thing, like plus or minus 20 years. So at this point, so we can represent everything with binary, and we think we won, right? We think we can get to a point where we have 1, 1, 1, 1, so on and so forth, all the way to infinity. But then you can do some weird stuff, right? Then you can take all the ones and you can replace them with zeros, right? So this already maps all the natural numbers onto binary or onto sequences. But we can also do that over again, and I call this star, although we can also have weird sequences where we have our ones and zeros alternating, and then we count with binary by reversing these. Or we could also do some weird stuff where we have another sequence where it's ones and zeros alternating, and then we count binary by reversing this, so on and so forth. 1, 0, 0, 1. So at this point, we can already do an infinite number of things, right? But we can add on to this. So if we do the p-adics now, and we think about p-adics, right? If we have 1, 0, 0, 0, 1, 0, 1, whatever, and then it continues this way, right? If we just reverse the direction. Now we can think about decimal representations. And if we can think about decimal representations with p-adic binaries, then we can actually show that we can kind of map this onto the real numbers, which are uncountably infinite. So with that, I've shown two different proofs for the same concept, or for the same thing, that our set C is uncountably infinite. And for a callback, we're gonna do a pirate-themed proof, matey. So here we have the C, and then we have our binary ship. There we go. There's our binary ship. And here's our last proof, right? So on this binary ship, we have a 1 and a 0, right? But this is no ordinary ship. This ship is Hilbert's Hotel on a boat. So we have infinitely many rooms. matey. We have infinitely many rooms. And another way that we can think about this is that we have 1, 0, 1, 1. These are inhabitants of the rooms. And let's say we want to plunder the ship with our infinitely sized crew. So here we are. We don't have a... there we go. Here we are. And there's infinitely many of us, right? And we want to plunder the ship. But here's the thing, right? We can obviously do this because we can, we have a uncountably infinite amount. Although with the Hilbert ship, this is so silly. Oh my gosh. But if you think about it, because we have an uncountable amount, whenever these look like little cannons. Whenever we add a new person, we can either add it just like that, and then we could move everybody else around. Although the thing is, we can't define a bijection to the natural numbers, right? And we see that with this sequence because we can just go diagonal. And if we think about all the possible combinations and we just go diagonal and we reassign the rooms in another combination, and then that shows the same exact thing. So really this was the same exact proof as that one, but we proved that the C was uncountably infinite. Okay. That was bad. That was a bad pun. This went on for too long. But thank you for being an amazing professor. I hope you have a great summer, and I'm excited. I will hopefully take either a topology class or a number theory class or something from you in the next 3 or 4 years that I'm here. Yeah, well, thank you so much. Really appreciate it.